let me first welcome our next speaker, Professor R.K. Shukla, and briefly introduce him before we start our today's talk. Professor Ratnesh Shukla is currently an associate professor in the Department of Mechanical Engineering, Indian Institute of Science, Bangalore. Prior to joining Indian Institute of Science in 2009, he was a postdoctoral research associate at University of Illinois at Urbana-Champaign. He received his PhD in 2007 and MS in 2005 from UCLA and a BTech in 2002 from Indian Institute of Technology, Kanpur, all in mechanical engineering. His research interests are in computational and theoretical mechanics, high-speed multi-phase flows, shock accelerated bubble dynamics basically, and unsteady flows, drag reduction, and propulsion. Audience, with this very brief introduction about our speaker, Professor Shukla, let's welcome him for the next session of this talk. And Professor Shukla, you are very welcome to address our participants.
Thank you, Professor Patel, and you and all the organizers inviting me. So, shall I start sharing my screen then?
Yes, start sharing. We haven't shared that.
I hope my screen is visible.
Yes, yes.
So, since the theme of this talk was, this session was basically high performance computing, I thought I would talk on something which actually involves high performance computing and which the flow is such that by its nature it requires very high resolution, is computationally very demanding. So it's an ideal platform for utilization of high performance computing tools basically. Okay. So in this talk I'll talk about simulations of multi-component compressible flows, and these are actually ubiquitous in nature. So if you look at ejection of a volcano and the kind of gases that come out of it, the particles, it's a particle and gas laden flow which is very distinct from the ambient. So it's a very common example of a multi-component flow, and this ejection takes place at a relatively high speed. So the flow is compressible as well, right? I mean, later as after the ejection, once the jet expands and so on, you may enter into a relatively low speed regime, but right at the point of ejection, the ejection speeds can be sufficiently high for compressible effects to be important. So we'll see this is one of the examples, but we'll see several more as this talk progresses, and these kind of scenarios where one gets very high speed flows in nature alongside multi-component behavior, where you get a lot of different components sitting together in the same flow field, is very common. So these sort of applications are also common in technological areas. So again, we'll see a lot of those, especially on cavitation bubble dynamics later on. But just as an example, I've shown here what happens when a jet undergoes, during its flight, goes from subsonic to supersonic flows, basically. It transitions from a Mach number which is less than 1 just to a Mach number which is slightly above 1, right? We get essentially a sonic boom, and in that sonic boom, because of the expansion that is created, one can have this sort of vapor formation, as you can see in this picture taken from Wikipedia. So the particular application that will be of interest here in the present talk is on cavitation, basically, and this is something which I think most of you would be familiar with. when we have very high speeds that are attained in underwater scenario, for instance, due to a rotating propeller as shown here, right, in this picture. I hope you can see my cursor.
Yes, sir, it's visible, sir.
Thanks. So if you look at this propeller as it undergoes very high speed in an underwater scenario, at the tip of this propeller, velocities are the highest and therefore the pressure is the lowest. So at sufficiently high speeds, this pressure can drop to such low values that one gets cavitation inception. Basically, the water here changes to water vapor, and then you get a helical distribution of bubbles that goes along the downstream as shown here. So these bubbles actually tend to be very susceptible to any pressure changes. So if there's a change in the pressure in the surrounding medium, these bubbles respond to it. They undergo shape and size oscillations, and they tend to collapse. Once they collapse, by collapse I mean they shrink a lot. There's a lot of energy that is concentrated as the shrinking takes place, and then they suddenly explode. So this collapse and sudden explosion, as I am putting it right now, would lead to formation of shock waves, formation of very high-speed jets, as we'll see in the coming few slides. And this is actually a high-speed multi-phase flow scenario. And this jetting and shock formation is known to cause a lot of pitting damage in hydraulic machinery. So if you see this picture here, you start off with the brand new hydraulic machinery of this form. Over time, within this limited time period, actually what has happened is that significant structural damage has occurred because of this cavitation bubbles causing this structural damage. So the earliest interest in this phenomenon of cavitation bubbles was to actually understand how bubbles actually cause this damage, and hopefully through that understanding make changes such that this damage is minimized. So I'll just show how bubble collapse process actually is. So you can see here there's a laser generated bubble that is, let me just begin this, expanded, and then there's a jet that forms and it goes and hits this solid boundary that is located at the lower portion. So again, this animation is shown here. You can see there's a bubble that grows, then there's a jet that forms along the central axis. This jet goes and the bubble collapses, and this jet goes and impinges onto this wall that is at the lowermost frame, basically. So this jet is very visible in this experiment here. What is not so visible is the shock wave actually. So as this jet goes and hits the distal portion of the near wall portion of the bubble, there's a strong shock wave that is produced. This is because of the so-called water hammer effect. You have a jet that goes and impinges on an interface. It leads to formation of a very strong shock. And this shock and the jet both combined together are responsible for cavitation damage. So in fact, it has been argued that the pressures that are generated when this blast wave emission takes place because of the jet impact is so high that the local stress can be as high as 3 gigapascals. And this is enough to cause a significant structural damage. Right, and if we recall, we actually have a bunch of bubbles that sit here in this configuration in an underwater scenario. So each of them causing significant jetting and shockwave formation can lead to pressures which are actually much higher than this value. This is a single value that comes from a collapse of a single, right? I mean, when we have collective collapse, one can expect that the actual pressures that are achieved can be much higher than this value. Okay, so this blast wave emission is a very interesting feature. Actually, this bubble, as you can see from these frames here, this blast wave is more clearly shown here. We have basically a bubble shown in this black region in this frame that my cursor is currently pointing to. This bubble starts to collapse, and you can see these black lines here, right? These black lines are actually shock waves, basically. These are density gradients in water, and these are shock waves that are generated because of this collapsing bubble. So this bubble clearly leads to emission of these sound waves and blast waves. And right on the other hand, what's actually causing this collapse? It's the pressure perturbations, which are themselves in a way sound waves. So bubbles are both sources of sound. They produce sound, and they also interact with sound. So this is a very complex nonlinear phenomenon, basically. Okay, and understanding this phenomenon requires both careful experimentation, and we will worry about the numerical simulations also in the coming few slides. But let me just talk a little bit more on the bubble collapse process itself. So because of its relevance into cavitation damage, there have been significant studies that have looked at single bubble scenarios. So, people have seen, for instance, how this bubble, in controlled experiments, how these bubbles grow and how they form the jet. They have found interesting features such as formation of a counterjet. So not always does this jet form only in the direction of the wall, but there can be a counterjet also. Then what has been looked at is what are the features of shock wave emission, what kind of erosion it can cause. And more recently, there has been investigation on cloud cavitation, basically, right? We don't have generally just a single bubble. We always have bubbles that feature in a huge collection. So when they are in a collection, how do these bubbles actually collapse? What are the features of this collapse? What are the shock waves that are produced, blast waves that are produced, and are they higher than a single one, or are they lower than a single? In which scenarios are they higher? In which scenarios are they lower? So these kind of questions are the key questions which drive people towards this cloud cavitation investigation. By the way, if you have any questions or any queries, please feel free to interrupt me. So till now I have actually only talked about how damaging this entire process is, right? I mean, it's a process which seems like we should try to avoid as much as possible, but that's not the case. Actually, one can actually try to control this cavitation process also. So there are advantages. This is a very fast and intense process. So the entire collapse process for something like a millimeter-sized bubble takes only a few microseconds. So that means that if it's that intense a process, which involves compressible effects, so the speeds are very high, we can possibly use it to actuate very small scale flows. So there have been proposals for these kind of activities, and here's one of them. You can see that there's a patterned surface here, a grid, hexagonal grid, and on this grid, people have actually tried to grow bubbles in a very controlled fashion. Okay, so bubbles grow only on these grids, essentially on this patterned surface, and once they grow, they also collapse in a very controlled manner. As you can see, they collapse such that a jetting flow is directed towards the center of this entire grid. So if one has confined geometries, for instance, what is shown here, you have something like a bubble that grows inside these walls. It can be triangular in shape, square in shape, and so on. You essentially get a very patterned shape of cavitation collapse. So the jet that is formed is not necessarily directed at the wall. It can be directed away from it. It can be tuned, basically. So this kind of flow, if it's controlled, can be tuned such that one can activate flows on a microsecond time scale. So there's possibilities of microfluidic applications there. Interestingly, actually, one finds I mentioned about multi-component flows being very relevant in nature, right? So not only that, this cavitation bubble dynamics is also something that can be observed in nature. So here's one example of it. If you would have heard about snapping shrimp, it's basically also known as piston shrimp. And this organism essentially draws its claws together, and then a moment later, the prey on which it attacks basically is stunned. So earlier, people used to think that this snapping shrimp actually kills using sound waves, basically. So it brings its claws together very fast, and there are sound waves that are produced, and those sound waves go and stun the prey, and the prey, is basically is killed or whatever, basically, right? So that was the essential idea. But what has been actually shown in around 2000 is that once this organism brings its claws together, there's actually local cavitation inception that takes place. So if you look at this, I hope this animation is visible.
Yes, sir. Yes, we can see it.
Okay. So you can see that as this organism brings its claws together, you get a vapor pocket, basically, because this is a very high speed action. There's this vapor pocket that is produced. This vapor pocket is unstable, and you can see it has collapsed, and there's a jet that has formed. So again, here shock wave emission because of this collapse process, and the jet are responsible for basically the action that this snapping shrimp wants to do, basically stun the prey. It's not actually the sound waves that are directly produced by bringing together of these claws. It's this cavitation bubble dynamics that goes on. And in fact, just as a cool thing, there's a reference of snapping shrimp in Hollywood as well. This was, I think, very recent movie where the actor actually goes on and says that the strongest organism, or rather animal on this planet, is not actually lion, it's the snapping shrimp, because of these stunning things it can do. Okay, so yeah, that's that. So I mostly talked about the experimental part and what actually is observed in nature. What we really want to do is understand and analyze this intense process using simulations. Right. So that's the primary objective of this talk. How do we develop simulation tools that can accurately account for this intense and fast process? So clearly, this is a very multi-scale setup. You have water on one hand, air on the other hand. Water, as you would know, is almost incompressible. We don't really hear about shock waves in water, though they are always there. But water is so stiff that one normally thinks of it as being completely incompressible. It's not very easy to make to attain a scenario where water becomes compressible. But this is a kind of flow where this bubble collapses to such an extent that it's like an underwater explosion. So essentially, there are finite compressibility effects. Air, on the other hand, is a very different medium. Air is very, very compressible. So we are dealing with a scenario where a very, very compressible medium undergoes such an intense change that it is able to bring about compressible changes in a very, very stiff medium. Right. So clearly, a very multi-scale setup. Both the behavior of water and the behavior of air are very different, but they are all tightly coupled in this scenario. The collapse process is actually very fast. So as I think I have mentioned before, for a millimeter-sized bubble, this collapse takes only a few microseconds, and the pressures produced are extremely high. And once this bubble collapses, actually, the sizes that it goes to are orders of magnitude smaller than its maximum size. So if one wants to simulate this process accurately, one has to be able to resolve these bubbles that are collapsing, right? And you can resolve it when it's at its maximum volume, but imagine that as it is shrinking, its volume is undergoing a lot of change, and one has to be able to resolve this bubble even at its minimum volume, because that is when the intensity of the collapse process will be extremely high and the pressures would be the maximum. So these are some of some unique challenges that one faces when one tries to simulate a flow like this, basically. Okay. Not only that, most of these things that I talked about are all valid for a single bubble, right? But as I argued before, bubbles actually occur mostly in clusters. So when we are looking at bubbles in clusters, the scenario is even more complex, right? I mean, what we are thinking about doing for a single bubble has to be done for each and every bubble. There can be merger, there can be split ups. So all these various things that we know are challenging for any multi-phase flows are all there. On top of it, we also have challenges that come from the compressible side, right? Shock wave emission, sound waves, regions where speeds are low, regions where speeds are extremely high. So how do we go about simulating such a thing? Would be the main topic of this talk, basically. And I thought I'll mention about just before I go on. Is there a question? I hear some.
Participants, do you have any question regarding this talk till now? I think we can go ahead, sir.
Okay. So please, if there's anything that you seek clarification on, please go ahead and ask. I'd be happy to answer. So Kishore, before we move on, how is generally it's done? It's all one go, or you allow in between?
No, it depends on speaker's choice, but mostly the participant ask question at the end generally.
Okay.
At the end.
All right, sounds good.
Sir, one small question. You are talking about these bubbles. So when are these bubbles formed? If a aeroplane is flying at a very high speed, at a very high Mach number, maybe at 800 kilometers per hour. So is it due to that pressure and all that these bubbles are formed? Liquid. It's a liquid bubble.
No, well, when we talk about airplane, it's actually a drop, not really a bubble, if you think about it, because
Yes.
here condensation has taken place.
Okay.
Yeah, it's a different scenario. Here you have air which has water vapor in it,
Okay.
and there's an expansion fan that is created. Expansion meaning like you are think of you have air and you have suddenly increased the volume that it occupies. So it will undergo isentropic expansion, which means the temperature will drop, and if temperature drops below a threshold, you can get condensation. So this is more of a condensation effect, not really cavitation effect. Here, on the other hand, you have extremely low pressures that are created inside water. So here you have creation of vapor bubble pockets, basically. You have vapor bubbles, basically, that are created.
Okay, sir. Okay, sir. Thank you, sir.
So the two scenarios are kind of distinct. Any other questions?
Any other questions from the audience? Yeah, I think we can go ahead, sir.
So I mentioned briefly about the challenges that one faces, and I thought I'll mention about the state-of-the-art calculation. So this is a calculation that was done by a group not too long ago. And here the idea was that they wanted to simulate cloud cavitation collapse. So they simulated something like 12,500 bubbles, okay, a big cluster relatively. And you can see the number of elements that they have used. And this calculation was performed over 16 million cores. So really a high performance computing application. So we know that this is a challenging simulation, and let's think about what are the desirables that we want in this simulation. So some of the desirables that we want are we should certainly allow for large interface deformations. This bubble actually grows, it expands, there's a jet that is formed, and all this means that the interface of the bubble can undergo significant deformation. So that must be allowed for. There has to be interface capturing. There's certainly an interface that separates the bubble from the liquid. So we have to have interface capturing methods. We also need shock capturing methods. That is because during this collapse process, actually shock waves and blast waves are generated, right? So one has to have shock capturing capability as well. Beyond that, it's preferable to have conservation because we have shock waves and we also have interfaces. So it's preferable. It's actually not just a preferable, mostly like a requirement that one has to be able to conserve mass, momentum, and energy. Without this conservation, we will not get accurate treatment of shock waves. So this is more of a requirement. What's special beyond regular shock waves? So if you are familiar with shock capturing, you would know that once conservative treatment is applied, more or less, there are a lot of different techniques that are available now for capturing shock waves, right? Whether they are weak or strong. But what is really special about this particular scenario where you have water and air is that water is very stiff and air is not. So a shock in air, which is extremely strong for air, is like a weak shock for water. So the propagation speeds of shocks are different, and when this shock is going to hit a water-air interface, its reflection characteristics, its transmission characteristics, these are going to be very different. So it's actually a challenge to be able to accurately account for this wave interface interactions when the mediums are very different. Okay, so this large density and pressure ratios. So because shock in air is actually weak for shock in water, whereas a shock in water is extremely strong for a shock for a medium like air. There's a large difference between the properties of these two mediums. So one has to be able to account for accurate wave interface interactions in this case. So that's a very significant challenge in this setup. Not only that, we are looking at cavitation actually. So as somebody pointed out, how is this pocket of droplets formed, right? There also you have, when you look at, let me just go back here. If you look at this jet that goes through Mach 1 transition, you have formation of these droplets basically. Similarly, in this cavitation scenario, as this propeller blades rotate very fast, you actually have formation of these bubbles, right? So vapor bubbles. So you actually are creating a new medium inside this medium, which is water. So if one wants to actually go and do a first principles investigation of cavitation, one has to allow for the creation of multi-material interfaces as well, right? It's not always that you will start off with a bubble. You will have to allow for the fact that if the pressure drops below a certain threshold, you will get bubble formation. And not only that, one has to be able to ensure that the whole formulation that we take is relatively insensitive to constitutive loss. In other words, that this formulation should hold whether you have today one equation of state for water and tomorrow you decide that this equation of state for water is not enough for my purposes and I need to change it. So the formulation that we do should be such that it allows for this change basically. So these are some of the challenges that are very specific to this bubble collapse problem. So in this work, what we do is actually we take this so-called single fluid treatment, where the conservation laws, basically the mass, the momentum, The first two, as you can see, are the mass, then you have momentum and energy are written for all the phases that are present in this setup. So for both water and air. And these different phases are distinguished using this variable phi, which one can think of like the void fraction or the phase field, basically. Okay, this field is governed by the interface advection, a simple interface advection with the local flow speed u. And what we do is we allow for very complex equations of state to be taken into account, right? So the dependence of energy on pressure, density, and this phi can be as complex as possible, all right? So one can have, for instance, the so-called stiffened equation of state, where pressure is related to the internal energy E, the density, and this ratio of specific heats or the adiabatic exponent. So gamma is typically 1.4 for air. So one can have this kind of equation of state, or one can have even more complex ones, such as the Mee-Grunissen equation of state and so on. So the formulation that I'm going to talk about has the flexibility to be able to account for these different equations of states, basically. All right. Before we move on, if we look at this setup, now we have got interface that is going to undergo a lot of deformation, and also shock waves that are going to be produced, right? So one key thing here is that there's a strong jet that is formed that is not a discontinuous feature, right? A jet is actually a continuous feature, meaning a continuous feature is a feature which can be represented on a mesh, basically, right? Once you have a very, very fine mesh, you can represent a jet on that mesh. Whereas a discontinuous feature is a feature which cannot actually be represented discretely, right? Like a shock wave. Shock wave is like a discontinuity, and a discontinuous feature like a shock wave actually can never really be represented only discretely, right? If I put points like this, I cannot say that there's a discontinuous feature that just undergoes jump like this. I put more points, I will get better and better resolution of that feature, essentially. So this is a flow in which there are discontinuous features and there are smooth flow features. So one more very key simulation challenge in this feature is that we have the presence of both of these continuous and discontinuous flow features, plus three-dimensional effects, unsteady flow, and because this jet is very high speed, you can actually have turbulence as well. So before we go on and talk about ways in which we can treat the interface, what I'm going to do is spend some bit of time trying to talk about the treatment of the compressible flow aspects themselves. Okay, how do we manage to simulate a flow which involves this complexity at high speed, basically? Okay, so clearly there will be a vast range of temporal and spatial length scales, right? Once you have a bubble, the bubble is big, now it has collapsed, so there's a lot of change in the length scale. There are shock waves that are also produced, so a whole bunch of a whole range of length scales are possible here. And similarly, there's a vast range of temporal scales also, right? The bubble is big, but it collapses very rapidly. So there's a very short time scale for its collapse. And then once we have a shock wave emission, the shock wave is going to traverse very fast. So again, that requires us to have very, very small fine time steps to be able to resolve the propagation of this shock wave. So if you are familiar with I hope the audience, can somebody tell? I mean, would you be familiar with shock capturing methods, for instance? Things like Lax-Wendroff scheme and so on.
Participant, any of you are working in compressible flow and shock capturing techniques and all? You are familiar a little bit? I think need some basic introductions.
Okay. Sure. So yeah, if you if you think about it, if I want to represent a discontinuous feature on a mesh, that is a tough problem because any discontinuous feature, for instance, you think about taking a Fourier transform of a discontinuous step-like jump, you always get these wiggles basically, right? So, which are related to the Gibbs phenomena. So one very stringent requirement that is necessary for shock capturing is that the method should be monotone, or it should not produce new extrema, new maxima, new minima. Okay, and there's only a first order method which is guaranteed to be a monotone method. All right. So essentially, what happens is when you have basically a shock that is present inside your domain, first order method can be captured. On the other hand, when we have things like vortices and so on, I mean, I think we all would know that nobody likes to have a first order method, right? We all like to have at least second or, if possible, fourth order and sixth order methods, which can capture these turbulence, these unsteady vortices, wakes, and so on. So here the scenario is such that we have these unsteady vortices, plus we also have the shock waves. So what do we do? These two features are producing what is known as this contrasting requirement that I have noted down here. The shock requires first order treatment, whereas these unsteady flow features such as turbulence, propagating vortices require higher order treatment. Okay. We are not going to talk about these additional complexities. There can be chemical reactions and so on as well, but let's not worry about it for the time being. All right. And I'm just showing why this propagating vortices and other features are important. If you just look at a very simple case of flow past cylinder, we know that as Reynolds number is increased, you will start getting these smaller and smaller scale flow features, right? Here you can see, so once Reynolds number is increased from 200 to 2000, you get smaller scale vortices. The wake also becomes more complex. You increase it to 20,000, you get even more smaller features, and the wake is increasingly complex. So to be able to resolve this, one needs higher order methods plus sufficiently fine mesh also. Whereas when one has shock waves and interfaces, only a first order method is guaranteed to be monotone, right? Only a first order method can ensure that shock waves are captured without oscillations. So how does one balance out? How does one move forward with these two contrasting requirements? The idea is to be able to use what is known as weighted, essentially non-oscillatory treatment. So one ensures that, okay, I have a shock wave somewhere in the domain. Let's find out where that shock wave resides, and close to that shock wave, use methods that do not produce any oscillations. But if you are in a region where there are no shock waves, you use methods that are best for propagating vortices, turbulence, and so on, basically higher order methods. Okay, so this one needs to be able to reduce the numerical dissipation and increase the order of accuracy, and that is done through this Vinod discretization. So I'll just briefly talk about the Vinod discretization on unstructured grids. This is something that we have spent quite a lot of time with, so that we can move forward with this particular problem at hand. Okay, and let me just skip this slide and go on to the Vinod scheme, what it does really. So if you are familiar with the higher order methods, you would know that what they typically do is they just take a wider stencil and they try to come up with approximations that are based on data from each of these nodes. So if one has like a uniform mesh where in one dimension, where the data resides at I plus 1, I plus 2, I minus 1, I minus 2, and so on, then to construct something like a fifth order method, what one would do is take all these 6 data points and apply like let's say I want to come up with the formula for the derivative at this point, right? I can use polynomial interpolation or Taylor series expansion and come up with a formula for that. Okay? So this is the typical approach that is used for higher order method construction. But imagine that now we have a shock wave somewhere. So let's say there's a shock somewhere here between I and I+1, okay, somewhere here. And I'm interested in finding the value at this location. I can clearly not apply a full-fledged fifth order method because Taylor series expansion actually assumes that the function that is being expanded is sufficiently smooth. So if there's a shock wave somewhere here, that function is not smooth, and I cannot apply Taylor series expansion. So what I need to do in that case is just use I+1, and I+2, these 3 points. Okay. If the shock wave sits between I and I+1, I should be using I+1, and I+2. And if the shock wave sits between I+1 and I+2 somewhere here, then I should actually be using these 4 points. Okay. So this forms the basic idea behind a Vino method. Vino method actually what it does is it takes all possible combinations basically. So in a fifth order Vino method, what is done is these 3 cells, I+1, I+2, approximation is formed using these 3. Then an approximation is formed between using these 3 cells, and another one using these 3 cells. And if one finds that there's no shock wave in the problem, then all of them are combined to get a fifth order approximation. And if a shock wave is present, then only the ones which do not involve a shock wave are used. So that's the basic idea behind a Vino discretization, and the effect of this Vino discretization on accuracy is actually quite significant. So I'm just showing here results from a very standard test case. This is this involves interaction of a sinusoidal density wave with a shock wave. And while here it's not important to just worry about the details of the test case, but more about what it shows. So these black lines here on this plot show the exact solution, basically what one should get. And these dots, these circles and symbols basically they show what is the computed solution as a function of the order of Vino discretization used. So you can see with fifth order discretization, lots of these details are missed, right? I mean, all these are completely missed in this red, by this red open circles, basically. And if one uses the Vino 7, this one, some of it is still visible, but the peaks are not captured at all, right? With increasing order, with Vino 11, for instance, the results are far better. So even when discontinuous profiles might be present, it's advantageous to use formulations like these, which can attain higher order and still capture these shocks. Okay, that's the basic idea. So what we have done is, because cavitation problems that we are interested in can actually occur in complex domains, we have actually spent a significant amount of time worrying about developing methods that are well suited for these complex domain simulations. Okay. I hope this slide is visible here. So
yeah,
if you recall,
yes, sir, it's visible.
Sure. So if you recall, we had Learning equations of this form, which were conservation law equations. So they can be written in this compact form here. Okay, these are basically our conservation laws. And in a typical unstructured mesh finite volume method, what is done is these conservation laws are integrated over this particular cell, like the one shown here. And the change in this conserved quantity is figured out from the fluxes that either enter these phases or leave these phases, right? So that's the basic idea. So each of these conserved quantities is taken like known basically at a given time step, And then that known is updated for a future time step by figuring out what are the fluxes. So if I have the cell average and I want to compute the fluxes through these intercell locations, what I need to do is basically.
Sir, I think you are muted just a second back. Hello. No, your mic. Yeah, it's fine.
You cannot hear me?
Now I can hear you. In between it was stopped.
Oh, I see.
It's proper now.
Okay, all right. The screen is visible, I hope.
Yes.
Okay. So the basic idea is that we have these cell averages that are given to us. And what we need to do is basically figure out what are these fluxes basically, so that we can update these cell averages in time. And to update these fluxes, we need the local values of on these u's, basically the state variable. It can be density, it can be momentum, it can be energy, or it can be the void fraction, right? So we need these local variables along these interfaces, all these cell faces, to be able to update the cell averaged quantity. Okay, so that's the basic idea. And to figure out these fluxes, what is typically done is that a reconstruction operation is performed. So given these cell averages, we figure out what is the interface value basically. So that's like a reconstruction, because you have only the cell averaged quantity given to you, whereas you are figuring out how this entire field actually depends basically on the space, right? So that's a reconstruction operation. And after that is done and these fluxes are figured out, one can then get like a system of ODEs for these cell averaged quantities. U bar I here denotes the cell average over this cell or this cell and so on. So the index I runs from cell to cell basically. And once we have this system of ODEs that is given to us, we can apply any of the standard techniques basically, like the Runge-Kutta method or the Adam-Bashvart method, or any temporal integrator to integrate this system of equations basically. Okay, so that's the basic philosophy. Now figuring out the fluxes is a little bit tricky when it comes to problems which involve shock wave. Okay, when we have a discontinuity in the solution, one should be able to actually figure out what is the correct upwind flux, and only then the calculation remains stable. So to figure out the upwind flux, one actually solves the Riemann problem at the cell phase. So imagine if we had only an advection equation, what one would do is figure out whether U is positive or U is negative and take the correct side value, right? If U were to be positive, one would take the left value. If U were to be negative, one would take the right value, right? That's upwinding idea. Basically, you figure out where the wind is blowing and then take the appropriate value, which gives you a stable solution. Here, when there are shock waves, rarefaction waves, and strong compressibility effects, the correct upwind value actually depends on the Riemann problem. Basically, I mean the solution structure that emerges out of this this entire system. So that's why one actually tends to solve this Riemann problem at each of the interfaces and then figure out what is the correct upwind flux, which will make sure that the computations remain stable. Okay. Now, what are the advantages of this approach? The advantages are that once we figure out things using a sufficiently higher order method, the discontinuities are actually spread only over a few grid cells, and even if you have these features like these vortices that you can see here, right? These propagating vortices, they will be accounted for accurately because we are using higher order method close to these features. And the lower order method is only used whenever we have shock waves like these, basically. All right. So let me spend some time on the Vino reconstruction itself, because that's also a complex operation. It's not as straightforward, especially when it comes to an unstructured mesh. So a key operation here is that one would like to figure out what are these values of the state variable along all these interfaces given the cell averaged quantities, right? So I'll just illustrate this procedure on a Cartesian mesh. Let's say we have a cell distribution which is shown like here, and we want to figure out how does a given variable behave in this blue colored region, all right? And what we are given is basically cell averages over all these different cells. So we know the cell average over this particular cell, we know the cell average over all the pink cells and also over light yellow cells, okay? So the idea is that what we do is just like I had shown in the case of one dimension here, right? If there are multiple shocks, we only take whichever stencil is the smoothest. So the idea here is similar. Out of all these different possible stencils, we break up this big stencil into these smaller ones. So we actually have these smaller stencils over which we formulate second order approximations. This is relatively easy because we have 3 cells and we can use something like bilinear interpolation to figure out what is the polynomial interpolant, right, over these. And then we try to combine them to get a higher order approximation. Okay, so that's the basic idea behind this classical Vino method, and one has to actually ensure that this combination must be convex. So if, for instance, let's say I figure out the polynomial here, 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 and here, and actually the weights turn out to be negative, the weights in which these should be added together, then that is a problem. All right, and the computation of these optimal weights is also expensive. So the way in which I can combine these various what are known as candidate Vino approximations, meaning all these second order approximations, is not it changes from cell to cell. Is not cell universal, basically, right? If you think about it, this orientation of these cells can change, the dimension of these quadrilaterals can change. So this operation and the optimal weights that must be used to add all these combinations is not something which is universal. Okay? So how do we overcome this scenario? So in this case, what we have actually done is followed the more recent adaptive Vino approach, in which what is actually done is we do a nonlinear hybridization between a higher order method and a lower order method. So I thought I'll mention these things. This may not be very easily understandable at this stage, but this is, I think, important because in our approach, there's basically complete flexibility in the choice of weights. So what we actually do is, if we come back to this scenario that I had shown earlier, what we do is we take a fifth order method that can be formulated over this entire stencil, and we take a bunch of third order methods. We add them all together in weights that are all that can be suitably chosen, okay? And then use that approximation to figure out what we should do. So if we know that there's no shock, we directly use fifth order method. We don't actually try to combine third order methods to come up with the fifth order method. If there are shocks, then we apply each of these third order methods in an appropriate manner. And all this is done in such a way that the algorithm automatically decides which approximation to take. That's the basic philosophy. Okay. And I thought I'll just illustrate this for a simple Cartesian mesh. So if we have something like a cell here over which we want to figure out how the solution varies, what we do is expand the solution out in something like a Taylor series expansion. Here we use Legendre basis functions because of the simplicity that they give. All right, so the expressions tend to be less cumbersome, and actually the smoothness indicators tend to be very compact. That's the basic reason. And using these expansions, what we do is that we ensure that the cell averages over all these different cells, colored cells, match the average of this P, basically. And once we have that, we come up with these coefficients can be easily figured out, and one has the full approximation, basically. Okay. One also gets this smoothness indicator. So I talked about combining fifth order, third order, and these various order approximations. But how do we actually combine them, right? We need something to tell us whether there's a shock or there's no shock. And that is done through something known as the smoothness indicator. It's basically some of these various derivatives, all up to the highest order point. So if we have something like a third order method, we go from the first order derivative all the way up to the second order derivative, various possibilities. And if the solution is not smooth, one expects that at least one of them will blow up, right? If you have a discontinuity, you expect that the derivative across that discontinuity will be extremely high, right? So that's the basic idea. These smoothness indicators, as you can see, are such that they involve convex combination of the derivatives, and therefore if there's a discontinuity, that will show up in the smoothness indicator. Okay. On the other hand, if there's no discontinuity, one expects that this will be an order 1 quantity. Okay. So I'm not going to go into the details here, but this use of this Legendre basis function simplifies this smoothness indicator quite a bit. All right. And this very same idea can actually be extended to unstructured grids as well. So we may not find explicit solutions like this, but what we can do is we can formulate the entire problem like what is shown here, and one can come up with a system for finding the coefficients and solve it using the least squares method to get the entire system of these coefficients, basically. All right. And once the coefficients are deduced, again, one can have second order candidate stencils like these, basically, over which one can formulate a second order method and then combine them all together to get a we know polynomial. Okay, so that's the basic approach. When it comes to boundaries, there are complexities there as well. So if you think about typically what is done in computational fluid dynamics, if one has a boundary like this for a Cartesian mesh, it's relatively straightforward to just use ghost sets, right, to implement the boundary conditions. So if I have a no-slip wall, I can say that my velocity field here in each of these cells should be computed in such a way that I get zero velocity all along this boundary, right? And if I have another stencil like this, where more cells are needed, I can extend this process, basically. I can figure out the values here in such a way that the velocity here becomes all zero. Okay, so that's the basic idea behind ghost cell based construction. Now, when it comes to an unstructured mesh, things are much more complicated, right? We actually cannot just generate ghost cells like this. All right. So what do? I mean, one possibility is that we reduce the order of accuracy. We say that, okay, we cannot create these ghost cells, but what we can do is we can use incomplete stencils and reduce the order of accuracy to whatever we can do. All right. And then do our boundary treatment. But the problem with that is that if we look at any problem that involves boundary layers or involves features at the wall, our resolution will become limited. So that means our calculations of the skin friction coefficient will be off and so on. So this is not something that we desire. So what we do is that we use these boundary conditions that must be applied as constraints, basically. So we say that if this is a no-slip wall, all along this boundary, I should have zero velocities, right? So I can use them as constraints that I impose onto this reconstruction operation. When I'm figuring out what is happening to the solution inside the cell, I can add this constraint and then treat it in this entire reconstruction framework. So that is what we do when we have either homogeneous or Neumann boundary conditions of this form. It can be very easily adapted to our general framework here. Okay. And this entire Vino reconstruction process that I talked about was for a third order method. It can be extended to fourth order as well. So clearly, as you can see here, the stencil gets more complicated. You have to involve more cells because you have to figure out more number of coefficients to ensure that one gets fourth order accuracy. And that means that there are more bunch of candidate third order cells like these, basically 5 of them. And the process of reconstruction, however, almost remains the same. Basically, one again has these weights that can be applied to figure out basically the Vino interpolant, and one has these smoothness indicators that tell us whether there's a shock in the setup or not. So before we move on, are there any questions? I did go over this a little bit fast, so if there are any questions, please feel free to ask.
Participants, any question with this regarding this part? Sir, I would like to ask, as you said, the third order, but unstructured getting more than second is like a very tedious job. Like, so here you're proposing the idea where first we create the second order and then we extend further for the higher order using the basis of that the reconstruction, like polynomials.
Yeah.
Yeah. So the polynomial direction, if I understand, the third order needs 3 unstructured cells, right? At least.
It needs a lot more, Kishore, because you need to be robust, actually. So that is not something I talked about. On an unstructured mesh, there is a lot of possibilities of the arrangement of cells. So because you see, you may have a situation where there are none of these yellow cells at all.
Yeah.
Right. So you may have a cell which is only surrounded by these pink ones. So one has to be able to ensure that all these different possibilities are accounted for. But nonetheless, the coefficients that are to be determined remain the same. So 1, 2, 3, 4, 5, 6 coefficients. That means I should generate at least 6 conditions from the stencil that I have found. But actually, in practice, you require around 10. I mean, the common practice is to have at least 10 to ensure that you are robust. And the reconstruction operation is genuinely multidimensional. So you can see that the basis functions that are used here involve all x, y, x square, y square, and so on. These variables, basically.
Yeah. Okay, sir. I think we go ahead with the further part.
Sure. So once this spatial discretization is complete, there are various options for time integration, as I mentioned. So one can go with the traditional Runge-Kutta methods, like fourth order Runge-Kutta method or strong stability preserving Runge-Kutta method. Or one can also do this arbitrary derivative approach. So again, we are not going to go into the details of this in this presentation, but this is a well-established technique now. It's more like a one-step method where the spatial derivatives that are present in any solution, sorry, the temporal derivatives that are present are actually converted into the spatial derivatives. So it's in a way, if you recall your modified equation approach, it's kind of similar, not exactly the same, but it's kind of similar to that. You essentially convert all the temporal derivatives into spatial derivatives so that a one-step approximation can be used to integrate the equations in time. And the advantage with that approach is that it's very local. So that means because it's just one-step integration, it's very good for parallel efficiency. So parallel implementation of the code becomes simplified, and you can attain large parallel efficiencies, basically. Not only that, the approach is multidimensional because both space and time get coupled together, basically. So there are advantages of using this arbitrary derivative spatio-temporal integration, basically. Now, with this, I will just demonstrate some of the simulations that we have been able to do, and this is one of them, the first one. So a very simple test, accuracy test, just involves propagation of an isentropic vortex, or also a Taylor-Green vortex that you might be familiar with, in which you start off with a bunch of vortices, and as they interact, they become increasingly complex and can give rise to turbulence, basically a decaying turbulence sort of scenario. Okay, so the motivation here is that we would like to establish the accuracy and convergence rates, and also study the scalability of this entire formulation. All right, so this isentropic vortex test case is a doubly periodic setup, meaning this vortex just advects like this and then comes back into the domain and just continues to advect like this. So in an inviscid scenario, this vortex does not undergo any deformation, and one is expected to get back the same vortex no matter how many times you advect it. But numerically, once an integration is done, we expect that because of numerical dissipation, this vortex will undergo some distortion and dissipation in time. And how much it dissipates and distorts in time will give us an idea of how accurate the method is. Right? So this just shows that we actually get fourth order convergence rates in both the maximum and the L2 norms, basically. So the method that we have formulated is actually indeed fourth order, and this test just confirms it. So this is the Taylor-Green vortex flow, the one that I described here, and it is actually solved over this domain. This domain is, you can see, purposefully distorted so that our unstructured mesh formulation can be tested completely. And what we find is that if we compare our results with what is obtained from direct numerical simulations, our implementation is not too bad. So the dissipation rates that come out of our implementation are very nearly comparable to what comes out of direct numerical simulations. All right, so we also did some scalability tests. So looking at advection of the isentropic vortex test case, we find that if we go up to like around 10,000 processor cores, the scalability of our method does not deteriorate significantly. So we still get up to about in excess of 90% parallel efficiency, even at this large processor core count. So this approach works quite well, basically. We do get higher order accuracy as well as good parallel efficiency with this approach. And I'll just show some of the demonstration results. These are standard test cases that you can see. So this is one of the test cases, a Riemann problem. Basically, it involves a setup in which there are 4 quadrants like this, and each quadrant has a state assigned to it. And depending on what state it is, you get various flow patterns. So this is one of the test cases taken from a paper here, cited here. You can see that there's a vortex that forms in this test case, and this is the kind of result that we get. So you can see we do get this vortex. We have actually run it at reasonably high resolution. Not only that, we also get these Kelvin-Helmholtz instability patterns along this contact line. So these would show up only when the method is low dissipation method and the resolution used is sufficiently high. So the fact that we can capture this tells that indeed our method is low dissipation method. Okay. And in fact, with third order method, you don't actually get these. So we can run a fourth order Vino as well as a third order Vino, but you can see with the third order Vino, we don't get these many flow features because the dissipation is comparatively higher. So similar setups are possible. So you can see this is another one taken from a different paper. You get these kind of flow features where you have these vortices that are shared and you have these contact lines also. You can see again the amount of details that we capture is extremely high, much higher than what is captured here. And the order of accuracy used here is actually 70. And ours is a fourth order method, but obviously we are using many more grid points as well. That is a fact, basically. Okay. So almost for every Riemann problem that one can find in literature, we can see that our method captures and gives far more details. Right here, you can see what kind of details are captured using our method, and comparatively what is captured in the literature. Okay. So there are more challenging setups that can also be simulated. So I'll just maybe I'll skip this one. I'll just talk about flow path cylinder. So this is a Mach 10 shock propagation over cylinder. I hope you can see this animation. You can see here that not only does our method capture these various shock waves, but it also captures the unsteady wake that is formed. Right, this shedding of the vortices is captured pretty well. And this is a 3000 core calculation, so a reasonably large calculation.
Mesh applied here is structured, sir, or unstructured, the what we explained?
This. Let me come to that, Kishore. Okay, so I could have addressed that. It is actually unstructured, but actually because I was going to show this shock propagation through a cascade of cylinders, basically, I thought you would obviously see, right? This is, you cannot do a structured mesh calculation here. So it's obviously unstructured, and this just shows these colors show the distribution of cores, basically. So if it's a 4-core calculation, you would have something like this. But what we actually do is, a very large core. So this is a 64-core calculation, would look somewhat like this. Our calculation is actually based on 3000 cores nearly. And this is a similar problem like flow past cylinder, but here you have actually a cascade. So you can see again, we can capture these shocks as well as very strong vortices as well. Solution is non-oscillatory. Okay, so you can see very detailed wake patterns are captured as well here as well as here. I hope the animation was visible, despite our, despite the fact that we are doing it over internet.
Yes, it was.
So, was there a query?
Audience, anything would like to clarify here?
Okay. I'll just continue. So we have done a bunch of calculations, basically. I mean, just to test the fidelity of the solver. So this is like flow past a foil with a flap. I'll go reasonably fast over these. So again, here the mesh can be very unstructured. You can have a higher mesh density close to the foil, and these are the kind of flow patterns that we get. So when the flow starts, you get these shock waves that are formed. And then you also get these propagating vortices that travel over the surface and are shed into the wake. So a lot of these different flow scenarios can be computed. We can have a cascade of airfoils as well. So you can see formation of shock waves as well as these strong vortices, right? So there's flow that enters this cascade and then exits like this, basically. Because the primary interest is in actually showing getting on to the multi-phase part, let me just still show this one as well. So this is a test case in which this is a non-standard test case in the sense that there's complex geometry. You can see in this blue region, we basically have something like ambient air. We have a triangular inclusion somewhere in between. And we have an explosion scenario where this circular region consists of very high density and very high pressure. So as this setup is released, this is the unstructured mesh that is used in calculation. So once this setup is let go, you get formation of hotspots, basically. So you can see you have, these are the temperature contours. You get very detailed accounting of flows, and you also get shock waves here and hotspots, basically, regions where temperature is high. Right. So this technique can essentially, it's fully parallel, and it's fourth order accurate, so it's low dissipation and can be used on a large number of processor core counts, and it allows us to look at very detailed flows, basically. Okay. Now let me just move on to the compressible flow part. So the multi-phase flow part. So till now we have looked at the fact that we want to capture propagating vortices and shocks both simultaneously, and still use a higher order approximation as much as possible. What is special about multi-phase part? What do we need for that? And the key aspect here is that we actually need to be able to capture the interface that separates the two phases, right? And what is special about this interface is that it's a contact discontinuity. So one of the problems with this is that if we take a simulation and just apply the compressible flow solver to it and use it for multi-phase setup, the interface will diffuse over time. That is because the interface is treated like a contact discontinuity, and by its very nature, the dissipation that is added to make sure that the solution is stable will continue to spread this interface over time. And that spread is unphysical. That is not something which is desirable. In a simulation, if we start off with a bubble that is initially sharp, and then over time, just because of our bad numerics, it spreads, that's not something which is desirable, right? If it should spread if it has to spread, for instance, because of evaporation or mass diffusion. But if it spreads because of numerics, that's not something which you desire. So we spend considerable time trying to come up with methods which prevent this spread. Okay, so this is one of the reasons why we want to ensure that the interface does not spread. If we allow it to spread, even if we have some simple setup, so think of one-dimensional setup where you have air on the left, helium on the right, and you have this interface that advencts. Okay, so if we apply a typical compressible technique like what I had shown till now, one finds that then not only does the interface spread, you also get this spurious velocity jumps and the pressure jumps. So if the interface simply advects, one should have a constant density and constant velocity maintained throughout, right? It should not change at all. But that does not happen with the use of typical compressible flow solvers. Okay. And in case of air water, this problem is even more dramatic. So if we have air here and water here, what we observe is that within a few time steps, the simulation just blows up. Okay. So we have remedied this through various means, basically. Our solutions of this have been discussed in detail in the literature, and our method is one of them, which relies on this diffuse interface treatment. So what we do is that, if you recall our objective, when we initially talked about different methods, we said that one of the key requirements that we want to satisfy is that we want to allow for creation of interfaces, right? If the cavitation inception takes place, one has to be able to grow a bubble in the liquid. So that requirement can only be satisfied by this diffuse interface method. So for this reason, we went on with this particular method, and we also ensured that the interface does not thicken over time. Okay. So to overcome this problem of numerical dissipation, continuously thickening the interface and making it look somewhat like this in time, we came up with an artificial compression method, something like a conservative level set method, and we ensured that the interface thickness remains maintained throughout the simulation. Even though the interface is spread over a few cells, the number of cells that it is spread over remains the same throughout our simulation. Okay. So on top of it, this is more, what I'm trying to do is trying to summarize the kind of challenges that one can face and how one can overcome. Okay, so problems like these require integration of a lot of different techniques, basically. So this is another technique that one can integrate into this setup. So we know that in these problems, the bubble undergoes a lot of deformation, right? And it can shrink a lot, its size can vary a lot. So it makes sense to not just use a uniform unstructured mesh or a uniform mesh everywhere in the domain, right? Which is non-adaptive. One wants to do something like an adaptive mesh here, where let's say a bubble is sitting here and another bubble is sitting here. You would want to put more mesh points close to wherever the bubble sits, because that's where the most of the action will take place. So this can be done using something like adaptive mesh redistribution. Okay, so this is a technique that is added on into this flow solver, and it allows us to actually put more data points, more grid points, close to the bubble or close to wherever action takes place. So think of on your right, you have a uniform mesh which can be through a structured treatment or unstructured treatment, and one gets a density gradient which looks like this. Now I want to have more points close to this density gradient. I apply this adaptive mesh redistribution technique and ensure that I actually do computations on the mesh shown in the left. That's the basic idea. So I have mostly talked about numerical method in the compressible flow part, so I'll just skip this. The only added component here is the adaptive mesh redistribution part. With this, one can look at a whole bunch of problems. We have looked at one-dimensional setups first, so that we are confident in the solver. Here, one can get an analytical solution. So you can see here we have a shock in water that goes on and hits an air interface, air-water interface. So after the shock hits, shock is transmitted into air. This shock is weak, as I talked about before, right? I mean, it won't be very visible because the density of air is much smaller than the density of water. But if you look at this exaggerated view, you actually get a shock. And you get a reflected refraction wave, an expansion wave that is transmitted into water. So this particular problem can be solved using our technique, and we get results like this. So if you see here, because we have ensured that our interface does not diffuse a whole lot, we get much cleaner results than what one would get if the interface were allowed to diffuse. So if the interface is allowed to diffuse, not only does it mean that you are diffusing the bubble, you actually get inaccurate results as well. This tail of the refraction tends to be erroneous. Okay. And this map here just shows how our mesh points are arranged. So initially, when we start the simulation, because there's a shock in water that goes on and hits the air, the mesh points are clustered close to the shock and also close to the water-air interface here. That interface remains stationary till the point at which it encounters the shock. Once it encounters the shock, more points are put both at the interface here. Relatively less points are put across the shock because the shock is actually weak, and there's a lot of points also in the refraction wave, right? Because that's also a strong feature. So overall, our technique works well in 1D, and comparisons with exact solutions are favorable. So we moved on and looked at 2D setups. This is like a very standard setup that is used in multi-phase flow community, high-speed multi-phase flow community. Shock in air hits an helium cylinder, which is placed here, and once it hits, a lot of wave patterns are created. So you get a transmitted shock wave, a reflected shock wave, and these shock waves inside this helium cylinder. And the cylinder itself keeps deforming, and it also leads to formation of a jet. This jet is actually less stronger than what you get in cavitation bubble, but still it's a jet nonetheless. And you can see, if you look at what is obtained experimentally, these results are qualitatively in good match with what we obtain using our numerical simulations, basically. So we have done collapse of air cavity. So this is like a cavitation bubble test case. Here we basically have on the top you can see density gradient contours, and on the bottom we are looking at pressure contours. So initially we have a circular region which contains air inside water, and once a shock wave hits this air bubble, the bubble starts to deform and then it undergoes collapse. You can see it has shrunk in size, and because of its collapse, this blast wave is produced. And the pressures here are extremely high. Okay, you can see that huge pressures are created, and this entire process of collapse is actually complete within a few microseconds, basically. All right. So our simulation can account for this extremely fast and intense process, and is well suited to do cavitation collapse studies. All right. This is another example. So cavitation is just one of the problems we can tackle. We can also tackle shock waves hitting, for instance. For some reason, it's not playing. Let me just check. I hope you can see this animation.
No, it's coming black screens. Now it is coming something.
Yeah, when I did full screen, I don't know why it. Okay, now it's visible, I hope. So you can see the shock wave goes and hits this water cylinder, and various wave patterns are formed. And our adaptive, sorry, again, it shows up as black. And our adaptive mesh actually conforms to the gradients of the flow, basically. So this is a generic framework which can be used for tackling these aero breakup problems as well. There are a lot of applications in which one is interested in knowing, for instance, how a fuel droplet that is pushed at a very high speed will disintegrate in air. So this is one of the setups that is relevant to that. As the shock wave goes and hits this water cylinder, the idea is to, I think I'll just maybe show this animation in this view if it's okay with you.
Yeah, this will be within last.
Yeah, I think these are playing in this mode, but not in the other one for some reason. So okay. So here, as this drop is pushed through high-speed flow, the idea is to figure out how this will break up. So this is not really something that is of direct relevance to cavitation bubble dynamics, but it's nonetheless a problem of interest. And these are also problems that can be tackled using our flow solver. So we can do multiple bubbles as well. So this is one of the setups in which we have a lot of different air cavities which undergo collapse. You can see as these cavities collapse, they lead to formation of these strong blast waves. And these blast waves are responsible for the damage that is caused to the surrounding structural medium, basically. And our mesh also conforms to the solution quite well. And you can see, just like the solution that was shown in the left, the mesh also kind of tells us what is happening to the flow field. Okay, so these ideas are extendable to 3D as well. So I initially talked about the fact that one has to be able to simulate very complex equations of state, treat them nicely as well, right? So this is like a full cavitation setup in which we have air bubbles sitting next to a copper medium. Okay. And there's a shock in water that goes and hits this air bubbles, and the idea is we'll see what happens to copper. Does it undergo any damage or not? All right. And these are the pressure contours for this setup shown along with the bubbles. You can see as this bubble collapses, it leads to very, very strong shock waves and also this jet. And on your right, you see this. Sorry, I think here again I will have to probably apply the original trick of playing it first. Okay. Let me try it again. I hope this is visible. These bubbles are collapsing, and then they have the bigger bubble has led to a dent in this copper water interface. So this dent is representative of the damage basically that these bubbles cause. And if you can see, there's some dent that takes place because of shockwave emission as well. So let me play it again. Right now you can see there's a small, I don't know if you can see this small feature here, circular feature, that's caused because of the shockwave. Then this bigger feature is because of the jetting. So both jetting and shockwave emission are responsible for damage. So this these simulations can be used to, as I mentioned before, they can be used to study something like drop shock interaction, aerodrop breakup, or even something like splash problems. So we have also looked at a splash setup in which we have full accounting of viscosity and surface tension effects. So here there's a drop that drops onto this pool of liquid. And you can see as it starts to move towards this liquid, because of its motion, a shock wave is created. So that footprint of that shock is seen here, the circular gradient. And as this drop interacts with this pool, it leads to formation of a crater, and then this crater grows, and this rim of this crater is susceptible to Rayleigh plateau instability. So that's why you see, because of the surface tension effects, you start seeing these undulations on top of this. So this solver is quite generic, and it can account for surface tension and viscous effects as well. And as of now, what we are doing is we are looking at ways of extending this to treat solids as well. If you recall the original setup that we want to look at, we want to actually study structural damage. So the structure is very much a part of this full setup. So one has to actually do fluid structure interaction along with multiphase flow to be able to understand how damage occurs to a structure. So we are looking at a comprehensive treatment of the structure as well, where we would like to model the structure using the full set of equations for elastoplastic flow as well as viscous effects as well. All right. So we are looking at a unified formulation as of now, and this is what we are trying to achieve. These formulations are also possible. So I thought I'll just mention that recently there have been works in which full elastic or elastoplastic solids interacting with other elastoplastic solids have come up. So you can see this is a simulation in which a red bar goes and hits a solid air interface. So simulations like these have actually become possible, and our hope is that in recent future we'll be able to use these to our advantage and to look at cavitation damage problem. All right, so let me just summarize what I have shown before we move on to the discussion. So I started off with describing about compressible multiphase flows, why they require higher order treatments, why they require treatments in which dissipation is low, the necessity of adaptive grid distribution, advanced interface treatments that ensure that the interface does not diffuse over time, treatments that can account for large density ratios. Then we didn't talk much about the viscous time formulation, but these treatments can be such that the integration in time is implicit. So so that the restriction on the time step is not too high. Right? We know that viscosity can bring in very stiff limitation on the time step choice. So implicit in time is good for viscous formulation. So our treatment is also fully parallel, so it scales well up to 10 raised to power 4 cores. It's really well suited for HPC simulations of compressible multiphase flows. And future challenges, we are looking at fully compressible unified setups in which we can simulate FSI and multiphase flows together. We are also continuously looking for advanced interface treatments. So the better the interface treatment, the more efficient our solver will be, and the more complicated cases we'll be able to handle. Right? So we are also looking at cavitation inception, how to ensure that bubbles can be grown in scenarios where there's cavitation inception. And this work has been possible through support from DRDL and DST, and a lot of different students have contributed to it. So Sundar, Dasika, Deepak, Vagani, they have contributed extensively through these developing these packages and tuning them to our needs, DL2 and PET-C. Quite a bit of it relies on Hyper and AMREX as well. So Mahesh, Savardikar, Preetham, Anil, and Professor Patel here, they have all contributed to our understanding of these packages as well. So with that, I would like to thank you for your attention, and I can take questions now.
Thank you, sir. It was really a very wonderful talk, and we have come to know about various like the up-to-date schemes and the work going on in the numerical side. So participants, if you have any doubt, anything you would like to share with Professor Shukla, please go ahead. Participants, please raise your hand, briefly introduce yourself and ask a question. Hello, among the participants. Till someone comes up, sir, I would like to ask some questions. Like you have shown that very beautiful the structure grid and its capability to handle different voltages and its structures, and I believe that code is kind of very much potent to deal with that some of the real flow over a turbine problem to that things and all. So,
Yeah.
With the fully turbulent TNS, I can say.
Mm-hmm.
So like such studies, anything like is going on currently, like something you're planning?
Not really right now. Depends on the application. If it comes through, if somebody is interested, that would be a good topic to take up. But because when you talk about turbine, right? I mean, you need to have the geometry first, and you need to be able to mesh it first, and it's very problem specific, right? Because turbine geometry and other things have to be meshed and taken care of properly. So yeah, I mean, certainly I think the code has that capability, but fine tuning that to the application at hand will require some collaborative thing where somebody is interested and then we look at that problem.
Yeah. So while discussing during my postdoc with Professor Narasimha and all, he was very interested to actually see those structures and how the vortex structure, reluminization, all those things happen. And he was very desperately looking for a very high fidelity code which can actually capture all these features. Right. Because models and all, like RANS models and all, they can't capture the details of structures.
Right. True. Yeah, so as you know, we have always been looking at methods which can do these kind of simulations and these kind of things. So this is a step in that direction, for sure.
Yeah, I believe
we can talk about this, sure, if you are interested or if anybody else also. Yeah.
Yes. So one more new thing I heard is ADER, like it's a one-step scheme, just like Adam Besforth and Moulton and all. So what is the typical accuracy we get in time marching in that? Like
the accuracy is the same as that of the space. So it's kind of like converting it into a modified equation. So it's the same as the space. If you are constructing a fourth order method, you actually think of expanding not just in space, but also in time. Okay. So you are actually, what you are doing is, you know the polynomial expansions, right? You are actually expanding in time as well simultaneously, and you are coupling the two in such a way that you find out the coefficients for the time using whatever you have done for the space. So it is a very unique way of doing things, yeah, and it's quite efficient. So it's more amenable to parallelization than RK methods, basically.
Yeah, like RK come up with the extra cost of intermediate calculation,
Yeah.
time calculation.
Yeah, so that hampers the parallelizability a bit, because each time you have to go into the sub-step and ensure that every calculation is, it's kind of, it's not really MPI barrier, but it is like that. Every step has to have a barrier, basically, before you move on. Yeah.
Right. And the stability point of view, I think people, the big advantage with RK is that it makes more stable than your Adam Westport or Adam Newton. So in that side, like how good is this ADER stability?
Stability is reasonable. Like CFL1, I would say, you would get CFL1. It won't improve with the order like RK, but it is not bad. Also, one has to remember that one is taking only one sub-step, right? So you are getting it done only in one single go. So even if the stability, for instance, you take RK4, if it's not 1/4 of the RK, then you are fine actually.
Right. Yeah.
And your parallel, your parallel efficiency has gone.
Intermediate steps compensate the smaller time size. That was very nice thing, sir. In fact, we as a student also we have come to learn many things new that is going on in the lab, and many new research front. So, audience, once again, if you're interested to ask any question, if any doubt comes to your mind, please feel free to share it with us. Share it with Professor Shukla. Anyone?
Sir, that we know method you had explained, different orders
Sir,
of
can you briefly introduce yourself, sir?
Sir, myself, Sajjan Kumar Lal, working as assistant professor in Tagore College of Engineering, Mumbai, Maharashtra. So my question was that Vino method of different orders you have shown, that is being developed by you, sir.
Yeah, some of it is being developed by our group, but the ideas are there in the literature. It's not
And
like
sir,
yeah. So
answer that. Answer that it was somewhat like sinusoidal in type in nature with different peaks. So isn't there any other method to study it? It looks somewhat sinusoidal, that graph you had shown. But the more the order of you take, the better results you are getting, isn't it? So, but it looks somewhat like sinusoidal. So aren't there other methods to evaluate that graph?
It's actually not sinusoidal.
Not sinusoidal.
No, it's not.
Okay.
It's the interaction of a shock with a sinusoidal perturbation. But because the shock is a discontinuity, the interaction is actually very nonlinear. So, and that's just a test problem. The idea is to show, let me just present it. Then I think it will be clear. I hope you can see this slide.
Yes.
So if you look at it, I mean, this part does look sinusoidal, but you see it's going up and down.
Okay.
Doesn't have a constant mean, and here you have a full nonlinearity, right?
Yes.
This part is not really linear. So it's not linear. Out here it's linear beyond this point. So here it was linear. The shock went like this, and it made it completely nonlinear. So if one wants to solve this problem, one can obviously put a lot of points and solve it. There's no issue with that. But the idea was to show what happens with increasing orders of accuracy. Is there an improvement? And we actually found that there is actually an improvement. So that means that there's value to pursue these kind of methods. Basically, that's the basic takeaway message, I think. Basically, I mean, if we think about more general problems like shock turbulence interaction, we will most likely get advantages there as well with these methods. or even shock bubble interaction. Yeah.
Okay, sir. Thank you, sir.
So thank you, Sajan. Any other doubt from the speakers? Sorry, from the audience side? Hello? Audience, would you like to, would you have any doubt, anything you would like to clarify? If not, then let's thank our speaker, Professor R.K. Shukla, for this wonderful talk and give us the idea about the update, like the various work going on in the field of unstructured grid. Mostly we are comfortable dealing with such thing in a structured grid, but adapting the such thing into unstructured grid comes up with a very different challenge, and that we have very in detail we have learned like what the challenges and how those challenges can be dealt, and the accuracy and the numerical challenges. So and thank you, Professor Shukla. Thank you very much for delivering this wonderful talk. Would like to address something, would like to say something to our participants?
Thank you all. I hope you found it useful. If you have any queries, anything comes to your mind, please feel free to ask even later through email. I would be happy to reply. And thanks, Professor Patel, for inviting, and other members and organizing committee at NIT Rourkela as well. Thank you. Yeah.
Thank you, sir.